it's relatively easy to put our impulse, F delta t equals change in momentum, to use right away. Consider a golf ball on a tee being hit by a club, and the ball is sitting still, v equals 0 on the tee, and the club is in contact with the ball for 0.0010 seconds, a thousandth of a second, and the ball takes off at a velocity of 70 meters per second. So according to Newton's second law in the impulse domain, we have the force that the club head exerts times the time, a thousandth of a second, is equal to the mass of the ball, and let's say that it is 100 grams. So we have 0.01 for mass times the change in velocity, which is 70 minus 0, or 70. So the force that the club exerted on the ball is going to be equal to 0.01 times 70 divided by 1,000th. So we move the decimal place twice, we get 0.7 times 1,000, and that's 700 newtons. No golf club could withstand that static load, but it's so brief, it happens so quickly, that the shaft bends maybe a centimeter or two and then recovers. If we were to apply 700 newtons of force to the end of a club by hanging a weight on it, for example, by having the club this way with the head here and the handle here, and we were to hang 700 newtons, apply 700 newtons of force, it would snap that in two. But again, the timing is so fast that the force will bend the shaft slightly, but nothing more. So that is one way that we see that we get a rapid solution. We didn't have to find the acceleration of the ball or use the big four. We're able to quickly determine what the force on the club head was as a result of our interpreting it, Newton's second law, in terms of impulse. Now let's put the delta t with the mass, so we get that the force equals m over delta t, and I can say change in mass, times exhaust velocity. So here's the rate at which mass is being consumed by a rocket. Let's say that it's 100 kilograms of fuel per second, and the velocity, we'll say, is 200 meters per second. So the upward thrust or force that we get for our rocket is going to be 100 times 200, so that's a 2 followed by 4 zeros. So we get 20,000 newtons of force. Now that's the downward thrust, which is reacted upon opposite and equally to push the rocket up with 20,000 newtons of force. We have to ask what the mass of the rocket is. Let's say that the mass of the rocket is 50 kilograms. So the downward force due to gravity, so here's thrust, equal and opposite, causing the rocket to go up, and the thrust is 20,000 newtons, and the downward force of gravity, with G being 10, would be 500 newtons. So the difference between these two is going to be the total thrust available for acceleration. So we get 19,500 is our delta force upward, and since F equals ma, the mass of the rocket being 50, by dividing this by 50, we get the acceleration of the rocket upward. So the acceleration of the rocket would be 19,500 divided by 50 kilograms, or 5 into 1950, which is about, I mean, if that were 2,000, it's in the vicinity of 400 meters per second squared, or 40 Gs. Obviously, we don't experience that. No astronaut would be able to survive that, even in a prone position. That's a very high acceleration. usually 7, 8 Gs are what an astronaut might have to absorb or be able to withstand in the launch of a rocket. So there are really basically two equations that we've learned about and just done quick examples of it, where we start with impulse and it equals the change in momentum. And this has two forms. We can use it for rocketry. If mass changes, if there's a change in mass, that's going to be thrust of a rocket. And if there's a change in velocity, that's going to be an impulse problem all the way to allow us also to find a force. We don't have a way, because we haven't had calculus yet, of allowing both the mass and the velocity to change. So we can't burn fuel off and change the velocity at the same time. We can ask what the initial acceleration is, but we cannot track the velocity of a rocket in time without differential equations. So we're not responsible for that. They're going to give us a problem, and we will know from the wording of the problem whether to hold the mass constant or whether to hold the velocity of the escape gas constant, both times allowing us to get a handle on the force or that's being exerted, for example, on a soccer ball by our foot, or the thrust, the gas on a rocket body. So that's our introduction to Newton's second law expressed as impulse. So we're heading toward being able to define work and being able to define and use momentum. And that's where we're headed toward understanding those, because eventually we want to be able to express the world not in terms of where something is. That's our big four. Our big four contain the distance and the velocity of the object, the time, and where it is, the distance, and we want to express it in terms of energy instead. So we're going to be able to look at problems in two different ways, in terms of the big four, where something is, and in terms of the energy, what kind of motion results for the object. And that's the direction in which we're headed as we continue to understand physics and get to doing more complicated problems, such as those that appear on the SSATs. But we're going to be so well prepared for it that you're not going to find them to be difficult at all. But I would add this to the list of equations that you memorize for the SSATs.